So we're now going to investigate the forces involved with moving around a banked curve. Now, every time you go in a corner on a road, you might not notice it, but they do bank the curve. It's basically to help. Very, very slight angles on roads usually, but it does happen. So I'm obviously exaggerating the size of the banking there. So all right, the road's banked at a certain angle and there's our object going around the corner. Let's put good old Bob in there. There's Bob. So what forces have we got? Well, now we've got a normal force. We're making contact with the surface of the road or whatever it is we're travelling on. So there'll be this normal, this reaction force. So sometimes you'll see it labelled R for reaction force, but N for normal force. The reason we call it normal force is because, of course, right angles. So we think the normal's at right angles to the tangent. So we've got that, but gravity is, of course, still there. That picture, when you think about it, is exactly the same as the conical pendulum. All that's happened is the normal force has replaced tension. And so what we see is all of these things also will become similar to the conical pendulum problem. So horizontal forces, so again, hopefully, because we don't want to be sliding up the road or down the road, we want to be staying in one spot. So we want to be moving in a nice horizontal circle, and those forces will be mv squared on r. And if we look at it, it's the normal force now into components. So we've got to work out theta. So again, I could play around with alternate angles and what have you to eventually come up with theta being in that position there, the angle with the vertical. So I'll get n sine theta to the left, but that's all we've got horizontally. So much like the conical pendulum, we get n sine theta is mv squared on r. And again, vertically, we're hoping that it's zero. We don't want the car jumping up or anything like that. And so we have a component of the normal force up and mg going down. We get n cos theta equals mg. Basically, the same equation, because now, when I divide, the normal force will cancel out, whereas yesterday it was tension was cancelling out. And we get the exact same little equation that we did for the conical pendulum. Tan theta is v squared on rg. So, all right, I bet you didn't know that train drivers had to do extension 2 maths, right? Because it's very important, because we don't want trains derailing. So it's even more important than it is for cars that they don't go sliding horizontally as they go around a corner, because they'll jump off the tracks and they'll make the news that night. Our railway line, circular curve, 400 metres. We know the distance between the two rails is 1.5 metres. And as far as the banking goes, the outside rail's 0.08 metres above the inside rail. We want to know how fast to go round to eliminate that sideways force. So we're not going up or down, we'll stay on the tracks. And next time you're on a train, just think of that train driver who's sitting there with his extension 2 maths going, right, for this corner, I've got to work it out. All right, that's the speed I'm going to travel at. You know? So all right, there's our little diagram again. It's the same diagram, but this time I'm adding in, well, okay, let's say the track's there down the bottom, one track, and the red one, there's the other track. So 1.5 metres, and there's 0.08 up. We'll place Bob there. Again, we have our normal force, our force due to gravity, and we'll locate theta so I can resolve the normal force. And we'll basically have the same equations we just saw. Horizontal forces is mv squared on r. We have n sine theta going to the left, so I know n sine theta is mv squared on r. Vertical forces equals 0, so n cos theta minus mg is 0. And let's eliminate the normal force because we don't actually know how much that is. So we now have tan theta is v squared on rg. Now, we know sine theta is 0.08 on 1.5 because with the dimensions they gave us, we've got opposite and hypotenuse. So sine theta is 4 on 75. Tan theta, well, working out the length of the other side, would be 4 on the square root of 5,609. Anyone got a calculator on? Someone work out 4 on 75. Someone work out 4 on the square root of 5,609. Let's see how close they actually are.
Very, 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 very close. So what was 4 on 75?
75 is 0.053 of theta. And then 4 on root 5609 is 0.05340.
Right. Now, the reason for that is our small angle theorem that we've seen. The limit as theta approaches 0 of sine theta on theta is 1. Or tan theta is sine theta on cos theta. So another way of expressing it is as theta gets closer and closer to 0, then sine theta and tan theta will have the same value. So in approximations, some people actually use sine theta rather than tan theta and say, oh, well, tan theta is approximately. Yeah. Obviously there's going to be a bit of error in that, so that's why I've worked out tan theta. But you might see some people just using the approximation, using sine theta, because, I don't know, they're lazy to work out tan theta. Let's sub it in. We know the radius, we know velocity squared, no, that's what we're working out, velocity squared. We know g we're using as 9.8. We end up with 14.47 metres per second, but that's 52 kilometres per hour. So our train driver can now go, oh, excellent, 52 kilometres per hour, I'll go around that corner, stays on the tracks, and everything's wonderful. Let's have a look at an HSC one. It's going back to 1995. Because the reality is, let's forget about the train tracks, although friction comes into play with a little bit with train tracks. But if you're on the road, there is another force there. Because if you're not going at that perfect speed, you will want it, just like the bob, want to rise or fall, depending on how fast you're going. Now, that means there's a resistive force, because anytime you move in a certain direction, there's going to be a resistive force in the other direction. That's where we now introduce another force called friction. So friction will go along the road. So you can see there it is. It'll be the same as the banking, friction. So here's our diagram now. So good old Bob's still there. The normal force is there, but now we have friction. Now friction's an interesting one. You'll see it's in the range of minus mu n to positive mu n. So sometimes it'll go up, sometimes it'll go down, all depending on how fast we're travelling. Because we're going too fast, that ideal speed, then we want to move up, so friction will want to oppose it and it'll go down. But if I'm going slower, then I'll want to go down, which means friction will go up because, again, we'll want to oppose it. So it could be negative, it could be positive, depending. Mu times n. Friction is always some constant times the value of the normal force. So we get mu times n. We don't need to know that. I mean, they'll give us that in the problem, but you'll always find whenever they quote it, it will be some multiple of the normal force, or should be. Either that or they just call it a constant, because if you think about it, mu times n is a constant. They've decided positive is going to be up the bank. So they've defined positive mu n to be up the bank. Acceleration due to gravity, we've got that. They've reminded us about circular motion, v squared on r, for the acceleration, and yes, it goes towards the centre. So basically, they've set up the problem. By resolving forces horizontally and vertically, which is logically what you would do anyway, we're going to end up, hopefully, coming up with that expression. So let's do that. Okay, I'm going to have to resolve both the normal force and the frictional force. So I have to locate theta in our triangles here. So theta with the normal force is there, which means that's 90 minus theta. So for friction, it's up the top there. We know all the horizontal forces will be mv squared on r. So horizontally, we have a component of the normal force going to the left, because it's going towards the centre. We said positive for friction was going up. So that's F cos theta going to the right. So we get n sine theta minus F cos theta is mv squared on r. So both of those forces should add up to be mv squared on r. Now let's have a look at vertical. Component of the normal force going up, component of friction going up. And the force due to gravity, which we now know is called weight, is going down. So n cos theta plus f sine theta minus mg will equal 0. So I'll make that equal to mg. Okay, the v squared on rg is mv squared on r times 1 on mg, which means I can just substitute straight in. I suppose it would have made more sense to go, hey, look at what we're trying to prove. n sine theta minus f cos theta. Oh, that's what I've got here. Over n cos theta plus f sine theta. Oh, look, that's what I've got here. So, well, I know that that fraction is equal to, so sort of like the reverse of what I actually did. Probably would have been more logical to go that way. But either way, you prove that v squared on rg is that lovely expression. Okay. Show that the maximum speed we can travel without slipping, so we don't want to be moving up the bank or down the bank, either way, is this one. So velocity maximum will be tan theta plus mu on 1 minus mu tan theta. Oh, by the way, you're allowed to suppose that mu tan theta is less than 1. Because I know that was probably bugging you. You're going, hang on. Oh, phew, we can suppose mu tan theta is less than 1. Thank goodness for that. Right. Here's my logic. It's friction that's resisting the particle moving up or down the slope. So if the particle is not slipping up the track, remember they defined up the track to be positive for friction. But if we're moving up the track, then the resistance is going down the track. So in other words, for this problem, F is minus mu n. The friction will be going down because we're trying to work out a problem about it travelling up. Got to be in the opposite direction. So for this problem, friction is going to be minus mu n. All right, so let's sub it in. Instead of writing F, I'll write mu n, which now means the normal forces all cancels. So I get sine theta. Now I've divided everything by cos theta, because look, they got tan theta in their question. So I'll change it to sine on cos, cos on cos, cos on cos, sine on cos, and voila, it comes out. Tan theta plus mu on 1 minus mu tan theta. So all we really had to do for this problem was substitute in friction. But we had to work out that that friction actually was the negative value we wanted to substitute in. Negative value we wanted to substitute. Okay. It's now saying mu is greater than or equal to tan theta. Show that if that's true, we won't slide down the track regardless of any speed. It will never slide down the track if that coefficient is greater than or equal to tan theta. So now we're talking about the minimum, and now we're talking about sliding down. So now friction becomes positive mu n instead of negative mu n, which basically means the formula that we just showed is going to be the same, except each term that came from friction, the sign will change. Because before it was negative, now I'm saying it's positive. So I'll get tan theta minus mu on 1 plus mu tan theta. So that's where the friction was before. We've changed the sign. We're trying to work out the minimum speed. Okay, they've just told me mu is greater than or equal to tan theta. Well, if that's true, have a look at the top of the fraction. The bottom of the fraction doesn't really matter. Bottom of the fraction is always going to be positive, because I've got 1 plus something. It's always going to be a positive number. But if you look at the top of the fraction, I've got tan theta minus mu, and we've just said mu is bigger than tan theta. So the top of the fraction has got to be negative. So in other words, v squared, the minimum on Rg, is less than or equal to 0. V squared minimum is less than or equal to 0. Well, it can't be less than 0. It's squared. So therefore, the minimum velocity is 0. Well, if the minimum velocity is 0, that's the minimum velocity. So anytime it has a velocity, it can't slide down. Now this one's an interesting one. We got a drum, a circular drum. Imagine one of those, big 40-gallon drums. Inside our 40-gallon drum, we have a ball bearing, and we're going to rotate. So we've got an object inside the drum, and we're going to spin the drum round. So that's basically what we've got here. Now, again, they're basically setting everything up, but because it's making contact, the ball bearing's on the surface of the drum, so we have a normal force at right angles to the surface. Well, surface is a circle, so at any instant, we assume it's like the tangent. If it's at right angles to the tangent, then it must be going towards the centre of the circle, because we know the radius is perpendicular to the tangent. So the normal force is heading towards the centre. We have the force due to gravity. We're also going to have a frictional force. Because when it's on that surface, again, there's going to be friction along the surface. So they've drawn all those in for us. What else have they told us? So they want us to resolve forces perpendicular to and parallel to OP. To find an expression for F on N. Because remember, the reason they've said that rather than saying horizontally and vertically is because this drum's rotating. Now it doesn't matter where I stop it, the forces are still going to be friction going off at a tangent, normal going towards the centre. It's still going to be the same picture. The only thing that will change is the direction of gravity, because it's always going to go down, but P will be in different position. So what I'm getting at is, let's make life easier and actually rotate it so that those two forces are actually horizontally and vertically. And it makes life a little bit easier. Unfortunately, gravity is now going off at a weird angle. But that's okay. It just means we're going to have a component of gravity. So if we're going to have a component horizontally, or what looks horizontal and what looks vertical, and playing around with our geometry, we can show that theta is there. Now, we're now saying forces, instead of saying horizontal, we're saying forces perpendicular to OP. And that's going to equal 0. Because the only thing that's happening here is circular motion. The way I've got my picture done now, that is purely what looks like a vertical force. Okay, so there's Bob. So what looks horizontally is we're going to have friction going to the left and a component of gravity going to the right. And they'll sum to be 0. So actually, I've got a little expression there that could work out friction. Now let's have a look, the ones parallel, or what now look vertically to me. And that is circular motion, which is directed towards the centre. So mr omega squared. That's purely vertical. I'll have a normal force going down, mg sine theta going down. So n plus mg sine theta is mr omega squared. Now, it was f over n they wanted. So, there we go. F over n, substituting in the two values that we've just found out, and we've got a beautiful expression there. The ratio of friction to the normal force, g cos theta on r omega squared minus g sine theta. This idea of rotating the problem can be really, really useful. Let's go back to that bank curve question where we had friction. So there's the bank curve. We had the normal force at right angle to the bank. We had gravity going down. And friction, well, I've got it going down in this case. I mean, it could be going up, it could be going down. Okay. I'm going to rotate the problem. So I'm rotating the problem, because remember, we don't know the normal force, we don't know the frictional force. If I leave it in the traditional position, when I come up with an equation, I'm going to have a component of the normal force and a component of the frictional force. So I'm going to have to use simultaneous equations to eliminate either the normal force or the frictional force. But if I do it this way, then when I do what looks horizontally now, normal force doesn't come into it. And when I look vertically, frictional force does not come into it. So I can get an expression to work out friction force or the normal force without having to worry about the other one. Yes, gravity now, I have to look at components. But the other thing when I've got this problem is this one, the resultant force. Remember, resultant force is purely horizontal, but I've rotated the problem. So my resultant force is now off at an angle. So I will have a component of the resultant force of what looks like horizontal and what looks like vertical. So here we go. Along the bank, so what looks horizontal? Well, the horizontal component of the resultant force will be mv squared on r cos theta. It's adjacent to the angle. Okay? So all those forces that look horizontal, well, what have we got? There's the frictional force going to the left, and there's a component of the gravitational force. So I know that F plus mg sine theta is mv squared on r cos theta. No mention of the normal force whatsoever. So there's a way I could work out the frictional force. If I now look at what looks like vertical, perpendicular to the bank, and the component of the resultant force for this one will be mv squared on r sine theta. So Bob, normal force completely going up, mg cos theta, the component of the force due to gravity going down. So n minus mg cos theta will be mv squared on r sine theta. And so I could come up with an equation for the normal force. I find that very useful. What I really hate is when they tie your hands and basically tell you to, resolve horizontally and vertically. Well, then I've got no choice. I can't rotate my problem. And so I'll end up with simultaneous equations and have to eliminate n and f and things like that. But if they don't tell me that, beautiful. Rotate the problem so that there's two things, normal and look horizontally and vertical. And all you've got to do is turn your test paper. There it is. Now it looks vertical and horizontally. But it does mean gravity will have components. But more importantly to remember, the resultant force now is no longer purely horizontal. There's going to be a component of it on what looks horizontal and what looks vertical. Okay, well, let's have a go at some of these. So there's Cambridge, the 9C, and Patel, the 9D.